So here's what we know and here's what we're moving towards. We started with a Riemann sum. A Riemann sum represented a rough area under the curve where we used rectangles and trapezoids to find that area. Then we learned that if I increase the number of rectangles or trapezoids to find that area, that we could get an exact value. That exact value is what we call the integral. The integral represents the area above or below the curve. So when area is above, it is positive. When area is below, it is negative. So if I have two areas and I'm adding their integral together, we would take the sum of the area above and subtract from it the sum of the area below. And that's what we worked on yesterday. Found an area under a curve from A to B, but at C, part of the curve went down below. So we looked at the area above and we subtracted the area below. We can also find area under a curve using our calculators. That's that Math 9 feature. That will give you the exact value. And then we also have this rule, which is what we're leading into today, which is constants can be brought out in front. So that's going to lead into our definition of an antiderivative and its properties. So 5.3 is antiderivatives. We're going to be able to calculate using the reverse power rule and reverse rules for natural log E and trig today. Tomorrow we're going to learn how, what if you don't know the function and you're given a whole bunch of areas, so it's kind of back to what we were doing. And then we're going to go to on the next day and we're going to add our mean value theorem. So we had mean value theorem for derivatives. We also have a mean value theorem for integrals. And again, same idea. Mean value means average. So it's going to be the average of the areas under the curves, or the average distance traveled. So the definition of a definite, and that's the key word, everything we're doing right now is definite integrals, is as follows. It is the integral of lowercase f of x dx becomes equal to uppercase f of x from b to a. And what we do is we take f of b and subtract from it f of a. So it's like that area above minus the area below. Or it's like saying, oh, I traveled 5 steps, but I started at 4 steps, so we have to subtract the 4 I had already added. Capital F of x is what we call the antiderivative. Capital F of x is what we call the antiderivative. So the derivative of capital F of x could be seen as f prime of x, but what we know is that capital F prime of x is really lowercase f of x. And again, all it's saying is if you integrate velocity, you're going to get position. If you integrate acceleration, you get velocity. So f of x was the function before lowercase f of x. So how do we find the most basic antiderivative? Well, we're going to find that using the power rule. So the power rule in reverse says that if you have a function x to the n, then its antiderivative is going to be that function, x to the n, plus 1 over n plus 1, which is that new power. So the antiderivative is x to the n plus 1 over n plus 1. So when we started calculus and we started derivatives, we started by taking the derivative of x squared. That was our most, commonly thought of derivative. So the derivative of x squared became 2x. So now we know we have this function 2x. And if I ask you to take the derivative of 2x, well, you take 1 away from your power, and then multiply by that. So if my power was 1, take 1 away, multiply by that 1, and we get 2. X to the 0, technically. So the degree of the derivative is 1 less than the degree of the original. So if the original is 2x, its derivative is 2. 2x is linear, 2 is constant, the degree is down 1. So if we think about 2x again, and we say, okay, well, what function got me 2x as its derivative? Well, that was our x squared. So if you take 2x and you apply your new power rule, the new rule is that you take the power it was, add 1 to it, and divide by what the power was plus 1. So that creates 2x squared over 2. But we know that 2 divided by 2 is 1. So we get x squared. So what that means is that if I took the integral or the antiderivative of that function, it becomes x squared. So the integral adds a degree back, or the derivative takes 1 away. So for now, every integral we're going to find is going to be bounded. So we're going to get a numerical answer. Every integral we're going to find for right now is bounded, meaning we get a number, or like the general number answers like yesterday. So 2x becomes 2x. Add 1 to it. Divide by that power. And then what you have to do is put the evaluation bars. So we are evaluating 2x from 2 to 1. So what that means is if you were to graph 2x, but you're finding the area under that curve from 1 to 2. So we could find it using geometry like we've been doing, because we know how to use the geometry. We know it would be a trapezoid of height 1, and then base 2, and base 2 would be 4. So you could find the area using a trapezoid, but now we can also find the area using our reverse power rule. So the 2's are going to cancel. And then what we're going to do is we're going to plug in the upper bound. So we're going to plug x squared and 2 into it, and subtract from it the lower bound plugged into it. So I get 4 minus 1, which is 3. And again, if I was doing this with geometry, it would have been 1/2, 1, 2, plus 4, which is 6, divided by 2, which is 3. So again, it's just like before, area under the curve algebraically is the same as the area under the curve geometrically, because these are easy geometric curves. Okay, number 2. We have 3x to the 5th, so 3x to the 6th, because you add 1, divide by that new power, minus, now we have 1. Well, that's really like times x to the 0. So what derivative gets you 1? Well, that's x. So this is going to become minus 1x, technically over 1. And again, you are anti-deriving from 0 to negative 1. It's always the top value plugged in minus the bottom value plugged in. So I'm going to take that 0 and plug it in. 3 divided by 6 is 1/2. So I have 1/2 times 0 to the 6th minus 1 times 0 minus 1/2 1 to the 6th minus 1 times 1. Anything times 0 is 0, so this all zeros out. And then I have negative distributing in. So 1 to the 6th is 1, so you have negative 1/2. A negative times a negative becomes a positive 1. So I get 1 minus 1/2, which is 1/2. So what that means is the area under the curve from negative 1 to 0 is 1/2. Since it's positive, it tells me that my curve is above the x-axis. R to the 1/2 minus 5. So again, antiderivative of a constant becomes linear. So this becomes r squared over 2 times 2. So again, you can't lose the number that is there. You have to multiply by it. Minus 5r from 3 to 1. So 3 squared is 9/4 minus 5 minus 1/4 minus 5. So it's 9/4 minus 15 minus a 1/4 minus 5. So 9/4 minus 1/4 minus 15 plus 5. So you can group together your fractions and your numbers. What's nice about 9/4 minus 1/4 is you get 8/4. 8/4 is really 2. So now I have 2 plus 5, which is 7. 7 minus 15 is negative 8. So what that tells me is that the area above versus the area below, it is more below than it is above. X squared is in our denominator. So if you go back and you think about when we took derivatives, if we had something in the denominator, we brought it up as a negative power. So for antiderivatives, we're going to do the same thing. We're going to say that this is equal to 1 to 2 of x to the negative 2 dx. So I'm just going to bring that x squared as a negative up. And then again, your rule is you add 1. So negative 2 plus 1 becomes negative 1. So you get x to the negative 1. And then we divide by that new power, right? So it's x to the negative 1 over negative 1 from 2 to 1. So you could really think of that as negative 1 over x from 2 to 1. So you can bring that negative exponent back down, and that negative on the denominator could actually go up. So now I have negative 1 over 2 minus negative 1 over 1. A minus becomes a positive. So I have 1 minus a half, which is a half. So number 6, or, well, your numbers are off a little, I believe, in the example just did. So your number 5, we have 1 over x. So that's the same as saying 1 to 5 of x to the negative 1 dx. And what happens if I add 1 to negative 1? Yes, and then I get x to the 0, and the rule is you have to divide by your power. So if I have x to the 0 divided by 0, are we allowed to divide by 0? No. So now you got to put those thinking caps back on, and you have to say, okay, when did I have a derivative equal to 1 over x? When did I take a derivative and my answer was 1 over x? Natural logs. So anytime you have a 1 over x or some manipulation of that, the reverse power rule will fail. So if you get that x to the 0 over 0, you're going in your head, no, natural log. So the antiderivative of 1 over x is the natural log. Now, natural log, by definition, its domain is x's have to be greater than or equal to 0. Like, you can't take the natural log of negative 1. So when you take the antiderivative of this, we have to say that it's equal to the absolute value of x. And again, we're evaluating from 5 to 1. So you have natural log of 5 minus natural log of 1. Now, once you plug in like the 5 and the 1, you don't have to write your absolute values because 5 is already positive. At this point, the natural log of 5 is a number. Natural log of 1 is a number. Technically, you could type it in on your calculator and get a decimal number. You could also do like the division rule where it's natural log of 5 minus natural log of 1. It's like natural log of 5 over 1. So, because natural log of 1 is 0. So technically, ln 5 minus ln 1 is really just ln 5. So the same is true if that denominator has an adding being added to it. So like if you have 1 over x plus 2, this is still a natural log. This is still a natural log. And this should still contain absolute values. That was my messy handwriting. So a natural log is going to occur if you have that x or an x like plus 1, x plus 3, x minus 5, like anything where you have a no power on top. Or if you have something adding or subtracting to the denominator. So you get natural log of 7 minus natural log of 3. And again, the rule of thumb is that if they're subtracting, it's division. Just in case it was like a multiple choice answer. So the other time you're going to see natural log occur is if you have a squared in the denominator and then 1 power less. So we're not going to get too many of these, but sometimes they like accidentally pop up on my worksheets because our textbook doesn't actually teach the antiderivative power rule until chapter 6, lesson 2. But yet they expect you to know how to do it for some of the assignments. So I kind of add it in, but when they have it, they don't have bounds. So like, I have to print and find resources for your assignments. So in case I miss deleting one, if you have an x squared plus 1, the derivative of x squared is 2x. You see that up above. Because if you go back, the derivative of natural log of u was equal to 1 over u times u prime. So if you see like that 1 over u, and then its derivative up top, it's ln. So if like the derivative of the numerator is, if the numerator is the derivative of the denominator, it's an ln. Yeah. Now, let's look at number 9. So we have 2 over x plus 3. So derivative of the denominator becomes 1. So this still follows that rule, because remember at the beginning of the lesson, I said that if you had a constant, you could bring the constant out in front. So technically, I could look at this as the integral of 2 from -1 to 5 of 1 over x plus 3 dx. So that 2 can be taken away, thus making the numerator the derivative. So you have to be careful with constants. So I get 2 natural log x plus 3 from 5 to -1. Now you might be looking at that bottom and going, wait, it's -1. We can't do the natural log of a negative. That's where what's inside the absolute values comes into play. And that's why we have the absolute values. Like let's say when you took it, it was negative, the absolute values make it positive. And in this case, you have x plus 3, so -1 plus 3 becomes 2, so it's also okay. So that 2 is going to get carried through to both terms. So it's kind of like the natural log of 5 plus 3 minus the natural log of -1 plus 3. And that 2 technically distributes to both. So we're going to end up with 2 natural log 8 minus 2 ln 2, or again 2 ln 4, because you have 8 divided by 2. So like lots and lots of answers. Now, number 10. This is from 0 to 1. Our denominator is x squared, but my numerator is a 1. The derivative of x squared, 1. So this is not a natural log. This is not a natural log. So if your bottom is x squared, but your top is not, it is an inverse trig. So this is tangent. And again, really, this is only if they pop up. Like our focus is on the power rule. But if you have one like this, if it has a square root in an x squared in the bottom and no derivative that matches up top, then it's an inverse like sine or cosine. But typically, so I think I put like on the one homework that it pops up on inverse sine or inverse tan next to it, so you just knew. So this is the inverse tangent of x. And then you'd evaluate it from 1 to 0. And again, inverse tan of 1 minus inverse tan of 0 takes you back to your unit circle. And it's, okay, when is the arc sine of tangent 1? So 5/4. You're in quadrant 1, it's positive. tangent is 1 at 5/4. And then, okay, when is the tangent 0? So that means you need sine to be 0, but cosine to be a number. So sine is 0 at, so you have 5/4 minus 0, or 5/4. I guess these are only if I miss deleting like some of them. Trig, I gave you like the antiderivatives without bounds on them, but the rule would be the same. So like if this was from 0 to pi, then you would have tangent of pi minus tangent of 0. So you'll just have numbers on these, but this is a great little reference sheet. It's also good to know, so like when you took derivatives of trig functions, if the derivative started with a c, then its antiderivative was negative. Now, if the antiderivative is equal to a function that starts with c, it's negative. So like the antiderivative of sine gives you negative cosine, because cosine starts with c. Negative cotan, negative cosine. So you have negative cosine x. So they kind of took the negative out of the problem for you. So if you look up at your chart, the antiderivative of cosine is sine. So the negative is just going to tag along. So it's negative sine x from 2 pi to pi. You get negative sine 0 minus a minus sine pi. Sine of 0 is, sine of pi is 3 of 0. So what that means is that the area under the curve of the cosine function that is inverted, so again, normal cosine goes like this. So now you've inverted the cosine function. And we're saying that the area under the curve of that cosine function from pi to 2 pi is 0. And again, that should like make sense, right? Because half of it is above and the other half of it is below. So the area above minus the area below cancel each other out. So again, my drawing is not to scale. So here, ignore the 9, right? The 9 is a constant. It's kind of like out in front. So you follow your rule from the chart. What is the antiderivative? And I thought ahead in my head. Of the sine of x. Well, antiderivative of sine is cosine. In this case, it's negative cosine because derivative of cosine should be negative sine. So we get negative cosine x, evaluating from 6 pi to 11 pi over 2. So 9 negative cosine of 6 pi minus a minus will become a positive cosine of 11 pi over 2. So then in your head you're going, okay, the cosine of 6 pi, where are you on my unit circle? So you subtract 2 pi away. So 6 pi minus 2 pi is 4 pi. Subtract 2 pi away. Now you're at 2 pi. So cosine of 2 pi and cosine
6 pi are the same, and they are at, or a value of 1. So you get 9 times -1 plus 9 times cosine of 11 pi over 2. So the only thing we have to be concerned with is 11 pi over 2 going to be at the top. That doesn't even matter. Cosine. So it doesn't even matter if it's at the top or the bottom, because the cosine of pi halves is 0. Cosine of 3 pi halves, 0. So cosine of any pi halves is 0. So, goodbye. My answer is -9. I was flying without my fill-in mix today, so I had to really reason through that.